In this video, I'll be talking about motion graphs, still under the topic motion under gravity. In my previous video lessons, I've used the mathematical approach to explain the motion of a body under gravity. When a body is falling from rest under gravity, or the motion of a body that is projected vertically upwards. We have derived or applied the equations of motion to them. The first equation, v is equal to u plus at or gt, and so on and so forth. A different perspective, and this is looking at it graphically. A graph is defined as a pictorial representation of information. It's a two-dimensional drawing that explains the relationship between two different variables. Usually we call these variables the dependent and independent. Dependent variable is always plotted on the y-axis, while the independent variable is represented on the x-axis. So here we are going to look at the velocity time graph of the motion of a body that falls from rest. And since the body falls from rest, we need to note that its initial velocity u is 0. That is, at t equals 0, the velocity is 0, which means that this graph will begin from rest, or we start from the origin. We'll start plotting the graph from the origin. Okay, so let's quickly do a sketch. I'm just showing you how to draw or how to sketch. I don't have my graph book here, but with this knowledge and understanding, you should be able to draw it on the normal graph book. Now, the y-axis, we have to label it the velocity axis in meters per second, and then the x-axis, we have to label it time axis in seconds. And the bodies start falling from rest, meaning the initial speed is 0 at time t equals 0. So we plot here. The graph begins from the origin. And let's see, how does the velocity vary? The equation for this graph is v equals u plus gt. Every graph has an equation. So we're going to see here there's going to be a linear graph, because u is 0, so v equals g times t. It means that the velocity varies linearly with time. And of course, you know that g is 10. So, which means if I'm to draw this graph, each time I substitute the value for time, I'm going to have the speed. For instance, if time is 1 second, the speed will be 10. If time is 2 seconds, that is 2 times 10, 20, speed will be 20. If time is 3 seconds, the speed will be 30. If time is 4 seconds, the speed will be 40. So with that, it will give us a straight line graph that starts from the origin like this. Okay, so let's call this point 1 second, for instance. Take it up here. This will give us a velocity of 10 meters per second. So when the time is 2 seconds, it gives us a velocity of 20 meters per second, and so on and so forth. Again, the slope of this graph, slope represents acceleration. Of course, slope has been defined as a variation, change in the vertical parameter over change in the horizontal parameter. So our slope is defined as change in the vertical parameter, which is velocity, over change in the horizontal parameter, which is time. And to be to find slope quickly, we just choose any 2 points on this graph line, on the trend line of the graph, and then we draw the slope triangle. Draw the horizontal, make sure this is parallel to the x-axis, and then take this, make sure this line is parallel to the y-axis. So we use this value, change in v, interpolate our change in v and change in t. This is my v2, this is my v1. So that gives me 20 minus 10 as my change in v, 20 minus 10, and my change in t is 2 minus 1. That is 2 minus 1. That gives me my change in t, 2 minus 1. That gives me 10 over 1, and that gives me 10 meters per second square. So since the slope represents acceleration, the unit of the slope will be meters per second square. So that's how to draw the velocity time graph of a motion of a body that falls from rest under gravity with negligible air resistance. Number 2, quickly, let's look at the displacement time graph. Displacement time graph of this body still that falls from rest under gravity with negligible air resistance. Now we have to bring out an equation that shows the variation of the displacement of the body with time. So from the second equation, we should have s equals ut plus half gt squared. Okay, so since the body starts falling from rest, u is also 0. So this equation simplifies to s equals half gt squared. So we can produce two different graphs from this equation. One, the graph of displacement against time. Two, the graph of displacement against time squared. Two different graphs. And then we have to bring out, okay, let's quickly look at how the graphs will appear. The first one is a displacement time graph. So I draw that here quickly, just showing you how to go about it. I'm not actually drawing it for you. So with the knowledge, you should be able to draw and also understand why the graph is like that. So this is displacement on the vertical axis, maybe meter, and time on the horizontal axis in seconds. So let's see, at time t equals 0, if we substitute 0 for t, it's got that s is 0, meaning that when t equals 0, the displacement, distance covered, distance falling is 0. So the graph must start from the origin. Yes, because at the time the ball is released, the of course the displacement from the equation is 0. So 1 second later, let's plot this point as 1 second. What is the displacement or distance falling by this body? After 1 second, we have s is equal to half times 10 times 1 squared, which is 1. That gives you 5 meters, because 2 here was 5, that is 5 meters. So 1 second later, the body has fallen a distance of 5 meters above the point of, that's below the point of release. So let's see again, when t equals 2 seconds. 2 seconds later, our displacement is half times 10 times 2 square, which is 4. That gives us 5 here. That is 5 times 4, which gives you 20. 20 meters. Let's say this is 5, this is 10, this is 15, this is 20. 20, just 2 seconds later, it has fallen a distance of 20 meters. That's the case where the body is falling with an acceleration. So this graph is not going to be a linear graph. It's going to appear parabolic in nature, a quadratic graph, because a graph of displacement or distance against time squared. So it will be a graph that curves continuously upward in the absence of air resistance. It curves continuously upward like this. It keeps on curving. So the graph is non-linear, 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 because the variation of the distance falling with time is not a straight line. We are plotting distance falling against time, whereas the time has a squared. So that's the behavior of the graph of displacement against time. Now, quickly, let's look at the graph of displacement against time squared. Number 3, how will it look like? Displacement against time squared graph, time squared, t squared graph. Okay. Um, how would this graph look like? Displacement against t squared graph. Let's quickly draw it. Now for this graph, the equation of the graph still displacement equals, since the body falls from rest, half gt squared. I'm plotting directly the equation of displacement or distance s against time squared. So which means that I will label my axis will be drawn like this. I have this, I have this. So which means I will label my axis as displacement against the square of time. Now when time t is 1, of course, what is t squared? T squared is t1. By the time I put 1 here, that gives me a displacement equals half times 10 times 1. Okay, so that will give me 5 meters. So when time is 1, of course, t squared is also 1. That will give me 5 meters. Now, when time t is 2, of course, t squared is 4. So that will give me, I'll plot 4 here. Let's say this point is 4, because when time t is 2, t squared is 4. So that will give me 20, because by the time I make substitution, I have, this is half times 10 times 4. That will give me 20. So I'm plotting 20 against 4. Instead of plotting 20 against 2, we plot 20 against 4. So by the time we finish plotting all these points, maybe using times from 4 and then 9 and so on, we obtain a straight line relationship between the displacement and the square of time. And the graph too, we start rather from the origin. So we obtain a straight line graph, the displacement times squared graph. Of course, we have to indicate the unit s squared. The displacement times squared graph is a straight line graph that starts from the origin. That shows that this is a straight line graph. The displacement varies linearly with the square of the time. Now, how do we define the slope of this graph? The slope of this graph will be given by the displacement by the acceleration, half acceleration. The slope of the graph is equal to half acceleration. How do I know that? We are plotting the graph of s against t squared rather, not t. So the coefficient of t squared is usually the acceleration. From the equation of a straight line graph, Fy equals mx plus c. So this is a general equation of a straight line graph. If a y and x were plotted, then m is the gradient or slope. So the coefficient of x is usually the gradient or slope. So the coefficient of t squared, which is what we plot on the x-axis, is our half acceleration, half a or half g in this case. So that I can find the acceleration due to gravity from this graph by multiplying the slope by 2. So acceleration due to gravity can be found. That is 2 times the slope of the graph. So I will do the normal way, go through a normal procedure of finding the slope of the graph. We choose 2 points, one here maybe, another one here. Draw your slope triangle as we did when we are calculating the slope for velocity time graph, and then determine the slope and then multiply by 2. That gives you the acceleration of the body. In this case, the acceleration of this body is going to be the value equal to the value of g, acceleration due to gravity, which is 9.8 meters per second squared. Okay, so we have seen these three different graphs. In the next session, I'm going to look at two other graphs, high time graph and high time squared graph.